In this video, we shall look at Newton's first and second laws. And let's start off with forces. What is a force? So let's start with acceleration. So we all know that acceleration causes a change in velocity. Right? For there to be a change in velocity, there has to be a non-zero acceleration. But what causes an acceleration? And that would be force. But we have to look at how many forces are acting and whether they cancel each other out. So what we can define this is that a net force causes acceleration, which causes a change in velocity. Alright, so this force is proportional to the mass of the object. And so this mass is the inertia, which is the amount of substance contained in an object, and it is a measure of the resistance to motion. So the greater the mass, the greater the resistance to motion, and the more force you would require to make that object accelerate at the same rate as an object with lesser mass. So let's look at the distinction between mass and weight. So mass is a scalar quantity, weight is a force, and so it's a vector quantity. Also, mass is a measure of the inertia by definition. It's measured in kilograms in the SI units, and this is measured in newtons, which is denoted by N. So the unit of force is the newton. Alright, and mass is a constant no matter where you take it, on Jupiter, on the Earth, on the Sun, in outer space, in the vacuum. Mass is always the same, and the weight depends on the environment. So weight is different everywhere on the Earth, on the Moon, on Jupiter, in outer space. It will depend on the gravity of the environment it is present in. Alright, so that's the distinction between mass and weight, and that's how we define forces. And so now let's see how a net force acts. So again, this is all vectors, so let's make sure that we are on top of our vectors. Alright, so let's say this is an object of mass m, and let's take right to be positive x, let's take up to be positive y. So now there is a force F1 acting to the right, so this force is positive. Let's say there is another force F2 pointing to the left. Now this is a negative force when we resolve it in the x direction. In what direction will this object accelerate? Or in other words, is there a net force acting on this object? And if yes, in what direction? Remember again that acceleration proportional to the force acts in the direction of the net force. And we'll see why that is in a minute. So in this case again, now these are vectors. So the net force, F net, and you have to add these forces up vectorially. So F1 plus F2. And now you resolve it along the x direction. So you will say that the sum of all forces in the x direction is F1, the component of F1 in the x direction, but in this case F1 is all of it in the x direction and positive x direction, so that is plus F1 to the right, and F2, all of it is along the x direction but along the negative x direction, so you have a minus F2. And you can see that F1 and F2 are pointing in the opposite direction, so there should be a relative negative sign between the two. And now we apply Newton's second law to it, which says that the sum of all forces is equal to mass times the acceleration. Again, independence of x and y says that the acceleration in the x direction and y direction are independent of each other, and we put this equal to mass times acceleration in the x direction because this is the sum of all forces in the x direction. Alright, so you get F1 minus F2 is equal to mass times acceleration in the x direction. In this case, there is no y forces, and that implies no acceleration in the y direction. So this is the equivalent of Newton's second law vector form. In component form, sum of all forces in the x direction is mass times acceleration in the x direction. Sum of all forces in the y direction is mass times acceleration in the y direction. Alright, so again in vector form, sum of all forces is mass times acceleration vector. So now you can see here that mass is just a scalar, so it's a number multiplying the vector A, and so the direction of vector A is the same as the direction of the net force, the sum of all forces in vector form. So the acceleration is always in the direction of the net force. Alright, so one consequence of this would be the statement of Newton's first law. So if sum of all forces is zero, which means if there is no external net force acting on the object, this implies that acceleration is also zero, which means the object will keep moving at constant velocity, which is the statement of Newton's first law. An object at rest or in motion at constant velocity will stay at rest or keep going at that same constant velocity in the absence of an external unbalanced or net force.